I think we're going to get started. Everyone here for the 802.11ac presentation? All right. Well, thanks for coming today. Today we're going to talk about a little bit on the overview of 802.11ac, a little bit of the history of how we got to where we're at today, indoor versus outdoor operation. Then we're going to get into the specifics of AC configuration in RouterOS and some of the new features that MicroTik has added to AC units. So, who am I? I'm the owner of Baltic Networks. We're a distribution, MicroTik distribution partner in the Chicago area. I used to be a WISP and ISP owner. Used to be ISP and then turned WISP back in 2003 and ran that for a number of years and then eventually turned that over to someone else. I have a little bit of experience with outdoor wireless environments as well as doing large-scale hotspot deployments. A little bit of the history. As you know, currently we started out with ABGN, 54 megabits, no problem. It's easy to do. You could drop any wireless card in and make it work. Then we had 802.11n, which most of you, I'm guessing, today are using in an outdoor environment in some form or fashion. Peak data rate's up to 600 megabits. Of course, that's the air rate. That's not your actual real data rate. How many doing well with 802.11n and getting like 300 meg type links in an outdoor environment today? You? Okay, so it's working out really good for you. So with AC, all right, 6.93 gigabits. That is theoretical maximum with the standards today. Obviously, we don't have that today, but that's with 8 spatial streams, maximum modulation, using entire 5 gigahertz bandwidth. That's really useful, right? So let's just use up everything. It's really not very useful, and quite frankly, I don't see it being used except for maybe some limited, like maybe video deployment in an indoor environment, yeah, a bunker, yeah, underground.
Away from our towers.
So that's what we have there today. Some of the usages, obviously, wireless displays, HDTV. There's already been demonstrations of like HDTV streams along with 4K video streams, again, in limited use with those higher bandwidths. Large up and downloads, good for point-to-point type traffic, campus and manufacturing and floor automation. So. What about AC and 5 gigahertz? Well, you'll notice there's no 2 gigahertz. 2 gigahertz doesn't have enough channels, so it's a 5 gigahertz product only. You have 25 non-overlapping 20 megahertz channels, and of course we have 80 megahertz channel sizes today, and 160 are coming. So 2.4, we're going to be stuck in 2013, and that's going to be the end of 2.4, maybe. Atheros, the chipset vendor that's used in most router boards, actually has a proprietary AC chipset working in the 2.4 band. I don't know if that you're ever going to see that product or not, but I don't know if you would want that. I would say keep 2.4 where 2.4 is today, and we may see the last of the technologies in 2.4, at least for the time being. So, as you can see, we have the 3 non-overlapping channels. We only have 83 megahertz of bandwidth, not enough. So we move into the 5 gigahertz. So, spatial streams and higher bandwidth. So I mentioned 6.9 gigabits. Here it is down here in this far right corner. This red box shows you exactly what we basically can do with today's technology and chipsets that are available. So we can do up to 3 spatial streams and 1.3 gigabits per second. You'll find that most of the shipping products today are 2 spatial streams using an 80 megahertz channel or 866 megabits. Again, this is air data rate, not your real packet throughput, but this is kind of like the comparing HDTV to 4K. So it is coming. It's not here yet, but it is on its way. So one of the main advantages, of course, is we get a different modulation rate, higher modulation, 64 QAM to 256. We have a 33% speed increase. What does that take to work? Well, you do need a client and an access point with the Wave 1 chipsets in order to make that work. So it is a requirement. There's an efficiency gain, and you'll see in another slide here that it's not linear. So as we increase the QAM modulation and go to 512, 1024, you're not going to increase the efficiency as much as you would expect. And it does require a higher signal-noise ratio in order to stay working. And then, of course, comes at a cost of distance. So have you all looked at a constellation diagram before or seen it? So we started out, this is the lowest modulation rate in 802.11n, BPSK. We got a 100% gain, we went to QPSK. Finally, we had another 100% gain when we went to 16 QAM. But when we go to 64 QAM, which is where 802.11 stops, we only had a 50% gain. Now we jump to 256 with AC, we're at 33%. As you can guess, as we keep going higher, we're not going to keep seeing those same gains that we would expect. Now, one of the gains that we do get is larger frame sizes. So 802.11n, up here, we had basically, you'll see down here, we had maximum layer 2 frame sizes of about 8K. Now, with AC, our effective frame sizes have jumped up to almost 12K. So we do have an advancement in frame sizes. You'll see in this diagram here, there's an overhead. You can see your overhead's the interframe spacing, a random back-off timer, then you have your PHY header, your MAC header, your packet, and another interspace frame, and it starts all over again. This interspace frame is commonly referred to as your guard interval. And you'll see later in the presentation, I talk a little bit about, we'll talk about the difference between short guard and long guard, but it does affect your bandwidth. So again, we're at Wave 1 today. This is called a Wave 1 chipset. We have our 33% gain. We're getting twice the capacity with our larger frame sizes, and we can do up to 3 spatial streams. And guess what's in testing right now? Wave 2. And Wave 2 includes all of Wave 1. We're getting those 160 megahertz channels you're all going to love to use in an outdoor environment, and 3+ spatial streams. This is the neatest one of all of them, is MUMIMO. It stands for Multi-User MIMO. And even though you're not going to use 160 channels, megahertz channels, you probably will want to use MUMIMO in an outdoor environment. And so what is it? It basically allows you to transmit in a single transmission cycle multiple downlink frames to different clients at the same time. It'll give you significant capacity enhancements to many single stream devices. So your iPads, iPhones, all that only have a 1x1 receiver in them, you have, let's say, a 4-stream transmitter. That 4-stream transmitter will be able to talk to 4 devices, single stream devices, all simultaneously in one transmit cycle, versus having to talk to four different ones 4 separate times. So that's where your efficiency gain is going to be. In an outdoor environment, let's say you have a 2x2 sector antenna, your gain would be really if you had a 1x1 client or a single stream client out there, so now you can talk to 2 clients at once. So far we haven't seen any efficient 3x3 antennas yet. We'll get into that a little bit too. So here's a visual diagram of what that kind of looks like. Again, 4x4 access point. Today, only talk to 1 device. in the future we'll be able to stream to multiple devices at the same time. So another cool feature for the WISP with AC over 802.11n is introduces this concept of dynamic bandwidth management. It's really good if you're using channel sizes greater than 20 megahertz. And the sweet spot in most of your instances, I'm guessing, will be 40 megahertz. Because what happens is in the 802.11n environment, and you have two channels. You have a primary channel and a secondary channel. The transmitter will send out a packet, and then the receiver, if there's interference on your secondary 20 megahertz channel, the receiver will not respond back to that initial packet to the transmitter, and the transmitter will resend that frame again. It'll just think it's completely lost. With AC, what will happen is if there's interference, the receiver will actually respond back on the primary channel saying, hey, I received it, but I had interference on that secondary channel. So it'll only retransmit the portion of the data that needs to be retransmitted, not the entire frame again. So there is some advantages in that regard. And as your channel sizes grow up to an 80 megahertz channel width, you'll get this particular type of advantage. The downside of this is that your primary channel can't have any interference on it. So you want to pick your primary channel as an interference-free channel. And your wider extension channels will be the ones that possibly might have interference. So to the specs, the receiver sensitivity changes from 802.11n to AC. With 64 QAM, you'll see we had a neg 64. And again, these are specs. These aren't router board specs. These are just the AC specs. With 256 QAM at full modulation, we go from 64 to 57. So, and that's a 20 megahertz channel. So you'll see that that means we need a higher power to basically run these types of higher modulation rates. The channel planning, this is kind of an overview. With AVG and then N, we've got the 40 megahertz channels. Then here's our 80 megahertz combined channels. The red channels here in the middle, these are our weather radar channels that you're not supposed to operate on. And then all of these, this interspacing here is all considered DFS-based frequency. So you got your lower, your upper. So, and you can see on our 80 megahertz channel widths, we only have 5 non-overlapping channels. That gives you enough for a four-sector tower and 1 backhaul. And you've blown through all your spectrum. So, I don't know how good 80 megahertz is going to be in a real live environment long term, but only your environment will determine that. So eventually in the 160 space, there'll be something called 80 plus 80. It'll actually let you split across the band and actually do 80 here and 80 up here versus having it all contiguous. So MicroTik has basically built all of their AC products along basically these two product lines. You have the 911 board, which they talked about this morning, the 922 board, which is with the, this is the net box, this would be the net metal product. And then finally, the 953 board is shown here. It doesn't have AC on the board, but you can use the new R11E board and put 2 of those on this board if you wanted to. That'll give you AC products. The 922 board, you'll see up here in this right-hand corner, there's a space missing. They actually can do 3x3 on this board, but currently shipping boards are 2x2. So the net metal, there is a 3x3 version of it where this stuff is populated. But for a board-only deployment, it's 2x2. We have a lot to thank MicroTik for giving ourselves, the do-it-yourself community, the ability to actually still build products using boards only versus actually giving us just a finished product like some other prominent manufacturers do. So this is still a very good solution for building your own setup. So outdoor signal and receive sensitivity. So let's kind of cover a little bit about if you were just to take let's say a 912 board, which is an 802.11n board on a point-to-point link, rip it out and put it in a 922 board or a 912 board, what are you going to have to do to make that thing work and keep it running at full speed? So with our 802.11n MCS7, this is we had the N board would have a transmit output power of 24 dBm and a receive sensitivity of -78. With the AC board, you do see we get a little increase in the transmitter output power. Receive sensitivity is about the same. Again, this is for the 300 meg 802.11n. Now we jump to AC, our transmit power is down and our receive sensitivity is down. So if we run the calculations and say we have a loss on the transmit power of 2 dB and on the receive sensitivity we're losing an additional 6 dB, our total loss is really about 8 dB or so. That's about the difference between a 2-foot and a 3-foot dish in some cases. So if you want to just be able to run higher speeds, you need to either plan on either making the link shorter or increasing the antenna size to compensate for that. 3x3 is a little more challenging and interesting because in an outdoor environment, so this diagram down here shows our vertical and horizontal component. Now we have a slant component. And the problem with this is it introduces cross-pole interference. And cross-pole interference actually causes the modulation rate to decrease. And so you really need a high isolation on your antenna to be able to maintain the same data rates on the 256 QAM rates or very strong signal. So you can cause self-interference in a 3x3 environment. So it's really best to look for antenna designs that have very good cross-polarity isolation. And you know, there's a few companies out there making antennas, and you'll find them next door here that have some really good isolation levels in them. So 3x3, that's why you saw this morning on the there was a mention of the dish where it may have had a third connector and it was removed or something like that. It's you know, it's a challenge. It's an engineering challenge to keep 3x3 running in an outdoor environment just because of that. You could put an antenna further up on the tower, another 2x2. So, but combining all three of those streams in one antenna is just difficult. It's really good for indoor use because you're bouncing off the walls and having different things going on in an indoor environment where packets are arriving and streams are arriving out of order, and it works really well, but an outdoor environment, not so well. So NV2, we've done all of our testing with NV2 on 802.11ac. Unless you need compatibility with a third-party product, I highly recommend NV2 if you haven't used it already. It's Mikrotik's TDMA mode that solves a hidden node problem. For a point-to-point link, NV2 isn't as necessary as it is in a multi-point environment. And actually, I have heard with the software implementation, there are some instances where a non-NV2 environment actually may be better in a point-to-point link. So you just have to try both and see what works better for you from a speed perspective. But generally speaking, NV2 works best. The latency is very predictable. So version 6.16 introduced 802.11ac. It was just July 17th, not long ago, so it is considered very new. They released version .18, which provided some minor fixes, and finally .19, which is the current shipping release, had improvements to the NV2 and AC protocol stack. So if you are playing around with this, you want to make sure you're running .19. That is in the wireless FP package. FP stands for fast path, and we'll talk about that here in a little bit. But that is the default wireless configuration on AC systems. If you do an upgrade and you're running just the standard wireless package, and you upgrade your system, You'll probably still be running the standard wireless, and if you change the wireless package to AC, or the FP package, you just need to make sure you change the other side as well, otherwise you may have problems with things working correctly. I know some people that have done upgrades and been caught in that, so. CAPS Manager, all this is going to talk a little bit about this tomorrow. This is really exciting, and the fact that it provides a really easy way to manage hundreds of access points by a centralized control system. It is template based. It works at a layer 2 or 3 level. You can either dump your traffic locally at the CAP, which sits at your client access point, or the manager, so it's all tunneled securely back. It is VLAN aware, and does require the wireless FP package. It's perfect if you're managing a lot of, you're trying to manage all these different channels and configurations at different sites, because you can basically template and push those templates out to your access points. So something to take a look at if you've got a lot of wireless access points. So the big changes in the channel width and terminology is on an end device, we had this thing called channel width that said 2040 HT above. Basically that meant you were on a particular channel and your extension channel was above that channel, or it might have said below. Now introduced is this C and E. And C stands for your center channel, E is your extension channel, and we'll show several different combinations of that here shortly. The 80 megahertz channels are now introduced, and you'll see now we have this C and lots of E's, and you're now going so fast that it says see ya. The yeah part isn't right now, you stuck that in there, but that's how that works. Finally, these are all your various combinations of center channel versus extension channels. So your center channel can be at the beginning, somewhere in the middle, or all the way at the end. And then all the E's fill in. If you're running a 40 megahertz channel width, you're just going to have one C and one E. And it can be above or below. So that's how you determine that. And again, if you're drawing that out, again, 20 megahertz block here, we have channel 44 as our center channel, and those all combine to get us our channel 42 at the 80 megahertz side. So one of the other things you can do is you can actually use the new FastPath feature. FastPath was introduced for Ethernet interfaces a while ago in RouterOS, and now with the wireless package, they have the ability to do all the queuing in hardware. So by enabling this, it actually jumps your CPU down considerably. So I would suggest if you're running the FP package to actually look at the FastPath function. It is supported in version 6.16 and above. So we'll cover a configuration example here on access point configuration as well as FastPath configuration. This is this access point up here and the configuration of it. We have, we're set on a center channel of 5765. All of our extension channels are above the center channel. In this particular case, I've selected 5 gigahertz AC mode only. You can actually have backwards compatibility if you need compatibility with older clients. But if you're just doing a point-to-point backhaul and you just want to basically run it full tilt and screen, set it to AC only mode. Here's where you set your wireless protocol. You set that to NV2. And that's really the majority of the basics of an access point configuration. Everything else is set by default in RouterOS you can leave alone. There's a lot of things you can do with the wireless configurations that I'm not going to get into in this presentation. But the station, you want to set your mode to station bridge. So we're in bridging environment. Again, AC. You'll see our channel width up here. Now, interestingly enough, in a station setup, you do not have to use an 80 megahertz channel on your station when your access point is set up for 80 megahertz. So you could actually run your station at a 40 megahertz channel, and it will only connect up to the access point using that 40 megahertz channel. So if you don't need all that bandwidth, you can set your stations lower than what your access point's running at. Finally, NV2 again, leave everything else default. If you want to run encryption on that link, here's where you set it. So on the NV2 tab of your wireless interface, you collect the security, put in your pre-shared key, you do the same thing on the station side, and now the link is encrypted. You do not use the security profiles for NV2. They will not work. So this is the place where you set up link. From testing with encryption enabled, it does not seem to decrease the bandwidth or the functionality of the AC device. Finally, we want to enable a bridge and set fast path on the bridging. By default, bridges now have allow fast path turned on, but you just might want to check it anyway, and that's in the settings function. Finally, in the bridge ports area, we just made sure that we have the Ethernet interface and the wireless interface. And testing, okay, it sounded like it died there for a second. So we got those in our bridge ports. Finally, we'll set up wireless fast path. Now, where do you find that? It's in the queues area. So you want to go over to queues in Winbox, slide over to interface queues, double click on the wireless interface, and that will pull up this tab here. You'll see there will be a drop-down box, and you'll select only hardware queue. By default, and you'll see over here, the default queue type is wireless default. So that's the only function you need to do to enable wireless hardware queuing. So finally, after that's all done, we can actually go over to the status tab of our client and see if we're connected or not and how we're doing here. Here you'll see up here our channel size. We're connected to 20 megahertz channels using our center channel, and it is AC connected. In this particular case, we were doing a speed test, so it was locked up at that 866 rate. By default, after you first connect up a client, they will only be operating at 6 megabits. This is a management frame. Management frames always run at the lowest speed possible until you start pushing traffic through the link, and then the link will increase in speed. So don't get worried if you're not seeing 866 right away. Start pushing some traffic and you'll see that jump up. Finally, we have our TX and RX signals. And in this particular case, we're down in the neg 20s. This is a very hot link. And again, it's because the units are so close. I was actually lucky to be successful at such a close range with this such of a hot signal, but it did work. Again, you want it a little higher than that. So our signal noise was up there at 84 dB, so it's really high. Finally, our quality indicator here shows, again, this doesn't really mean anything until you start pushing traffic through it. So we had a 97% on our transmit rate up here. So another note I'll mention to you on the TX and RX signal strength. These signal strengths are basically the 6 megabit or the management interface signal strengths. So just because you may be locked up at 866, you're actually, what's being reported here is the management, the lower modulation rate signal strengths. So just kind of keep that in mind. Not everyone knows that your real signal strengths at the higher modulation rates are actually going to be a little bit lower than this. So this is best case right here. So reading this line, if you never understood what this means, this is a little indication. So this is our transmit rate, our channel size. Finally, the second number, the 2S, means we're actually connected with 2 streams. A 3S would be a 3-stream environment. If there's nothing there, it's single stream. On the far right, this is our guard interval. So if it says SGI, that means we're operating in short guard interval. That's the most optimal configuration. But you may not see an SGI at all. If that's the case, we're in a standard long guard interval. And in long guard interval, you're not going to see a top 866. It's going to be a little bit lower than 866. So in summary, the best thing to do is to keep your signal strengths in the neg 40s and 50s, a low SNR, helps your modulation rate stay high. Don't overdrive the receiver, and yeah, neg 20 is considered overdriving the receiver a little bit. Use the lowest channel size for your application, obviously. It goes without saying, being a good bandwidth neighbor, just don't use those 580 megahertz channels and blow everything up and say I'm done. Finally, use fast path to decrease your system load. On the CPU, you'll get better performance out of it. And look for those high isolation port antennas. You'll have a better setup overall. Finally, for your rural folks, 8-mile CPs installs aren't going to work really well with this technology. You're going to want to keep it down to 2 to 3 miles if you're doing multi-point. I'm guessing a lot of you will probably test AC in a point-to-point environment first. That's really where it shines before moving into multi-point. So I'm going to show a little demonstration here if we've got time. Are there any questions so far before I move into a demonstration?
On the TDA MA frame size that you showed in that one frame, I noticed that on the wireless package there's a auto selection on that. Is there maybe Oldest or you could perhaps comment on what's the best configuration for that?
So basically, this new setting is called auto, or in Winbox it shows like nothing, so it means in auto. So it means that it's automatically dynamically changing from 1 to 4 approximately, depending on your traffic, and if you have a lot of traffic or not, and depending on how many packets you're sending. So it's automatically adjusting. If it's an idle link, it will you get like better latency, because previously static like the setting on the idle links, this latency was higher. Now it should be better. But sometimes if it would not be so optimal, sometimes you will still want to use like a static value. It depends on each location individually, what kind of traffic you are sending. So you need to play with that.
Thank you.
All right. Okay, so earlier you said that we do run rural ISP, so we have quite a few of those 6 or 7 mile CP installations. We have a lot of repeater sites too that we drop out to. Does the AC work okay when it's going to use their repeated link? If I drop one AC receiver and then repeat it back out of gigabit Ethernet to another AC, does it hold up as far as transfer path?
Shouldn't have any problems as long as, again, you're using different center channels and you make sure that your extension channels, you don't have any overlap in that environment. So, but you'll notice that if you just kept 802.11n and dropped in the new board in place, the new boards have a higher transmit power on them. So in theory, you should actually get a little bit of a performance improvement just with dropping the new board in place without jumping into the higher modulation rates.
A lot of our cards that are out there are still R52, like original
right.
non-input cards, so we're doing upgrades as we roll through, but until we get to that point, now we're like, well, should we just use AC instead of N modules and keep moving forward? So.
Okay. You'll see one of the things I wanted to point up here, this is one of the station up here. In the frequency, there's this auto mode, and again, it's the access point. It'll auto-detect frequency that's a center channel that's not being used. But some of them are highlighted in bold, and some of them are not. So in this particular case, the bold are the center channels that we can actually pick, and then the extension channels will, based on what configuration we have up here, will fall behind that. And this is, of course, your default scan list. So these channels are the ones you can choose for that. So.
With the lot wider, we're using a lot more bandwidth, and of course 5 gig is growing bigger. Is there any thought process on doing some sort of satellite syncing so that all the transmitters at one site transmit at one time and receivers, so that you can reuse frequencies, or at least not step all over yourself?
So what you're referring to, I believe, is GPS synchronization
Some kind of synchronization.
or something related to that, and that's
Currently not in the near future, so maybe later.
In the later future.
I may be a little out of date, but WDS not required on points anymore.
So one of the neat features with NV2, if you use the station bridge mode and the AP bridge mode in RouterOS, it does all of that configuration behind the scenes. So effectively, it's still WDS, but you just don't see it anymore. So you can still do WDS. There's still WDS in the software. You can still select it. You can still set it up. You can set up dynamic, static links, all that sort of stuff. But if you're just trying to do a simple bridged wireless network, using these new features, station bridge and AP bridge, and just adding them to a bridge group is the most simplest way to do it.
What happens if you get the extension channels changed up on the access point and the clients are different? Will they still connect up at the number of extension channels?
So the question, someone in here in the back there, if the settings here, this is the station we're looking at now. So if I've got this set differently, then the access point, will it even connect? Basically, is what you're asking. Yes, as long as you have you've selected an 80 megahertz channel, you're running 80 megahertz on the AP, it'll auto detect and set, I believe, the it'll detect the right center channel and connect, so you won't have any problems there. It's like finding the frequency.
Is that only on 80 megahertz? Does it work on 40 or?
It works on 42.
Well, I had a client that did that. We had it backwards and it just picked up 40 even though I figured it wouldn't.
Yeah.
I just was going to comment on his comments with talking about GPS synchronization. I know we have several different sites with not MicroTik equipment, with Ubiquity equipment, back to back. As long as you have good enough RF isolation, you really don't even have to worry about it. Because I mean, I have equipment that's maybe 8 inches apart, and I can run the same frequency and still maintain the signal noise ratio as well as noise floor of 103 on the one that we just did, and still use the same frequency back to back. As long as you've got proper RF isolation between the antennas. So, I mean, it just comes down to proper engineering.
Any other questions? We're going to see if we can fire up a test here really quick. Forgot to put passwords on these things. We have a lot of.
You don't trust us?
Yeah, we have a lot of tech people in this this crowd. So, all right, so let's see if I can slide this over while this is running. We can watch our signal. This is just your standard UDP test. Let's jump to the signal. So, okay, so it looks like it's changing around a bit. We're running 650 right now. Our speed test, we're doing 450 megabits. This is a UDP receive test. Now, one thing I will point out that is I wouldn't call it a big no-no, but I'm doing a speed test from this guy to this guy. MicroTik will tell you the best way to do a speed test is through the device, not from the device to the other device, which is correct. So if you really want valid numbers, drop like a cloud core router on the end of each of these things and then really pump the data through them. But in this particular case, we're using the CPU to generate the traffic, which is running our wireless. So we're taxing them a bit, but we have a little extra overhead now because we're running that hardware queue on wireless. And if I actually pull up the CPU right now, you'll see we're only running about 80% on the CPU, even with the speed test running, pushing that bandwidth right now. So it would drop down considerably after that. So you see it's pretty consistent. Again, we're running that 2-stream. We got that short guard interval going over here. Our signal noise ratio, of course, is screaming, and it's moving pretty good. There was another question over here.
Would you be kind enough to change that to TCP?
Sure. So we want to do a TCP test. All right. So we'll.
They'll crush the CPU like instantly.
Yes,
Well, yeah. So that's right. That is a problem. Yeah. So we can't. I can run it, but it will actually max the CPU out because again, this is where you really need to be using.
Why don't you add the CPU to the Winbox there?
Yeah. It's.
Oh, is it off to the side?
It's off the.
Or just rock this up there.
Can you add another one?
Add CPU.
There you go. There it is.
I am.
So, but I mean, we're still pulling. Well, yes, 160 megabits. So yeah, we're maxing this thing out. So.
But from device to device, that's not too bad.
Yeah. Another question way there in the back. Now, let me show you something too. So this is running, so I've got what I'll call an ideal polarity, vertical and horizontal. If we change one of these antennas, we just pop it up a little bit, you can actually watch our signal on one end drop. Now we're down to, yeah, it drops considerably just by changing that to that slant polarity. Now we've changed our isolation between those two antennas, and we have a significant drop in performance. So.
Okay, we got a lot more bandwidth going through this, but as far as packages per second, what can we look for?
In packets per second?
Yes.
I don't have any specific numbers. Maybe all this, I don't know, do you know anything? Packet per second values?
We don't have any such values, but if, for example, you can run like 100 byte packets in UDP, like, and you can try to do this test in UDP, maybe 100 byte packets, for example. And then you can watch the packets per second on the wireless interface.
So you'll notice one of the little bugs I found, when you're running the bandwidth test, you see the little graphs broke down here, it stopped running. If you close out the bandwidth test and restart it again, the graph starts working, but you can still see the numbers down here. So you see our CPUs right up here, yeah, 80s, 70s, 80s. We're doing 80, 90 megabits or so.
Maybe you can pull down with this bandwidth test so you can see the packets per second.
Which one?
You just go to traffic, Kenny.
On the wireless
Oh, here.
interface. Yes.
There we go.
Sounds like more than 100.
Yeah, it looks like 115,000, 100,000.
Is it enough or not?
Anything else? Anyone else?
Have you tried this test, this same test with the 3x3 radios?
I have not.
Okay.
Yeah, so we have not received those yet to even be able to try those yet. So,
Okay.
but all right, good. Well, hopefully y'all get a chance to try this in your live network. I'd certainly be, if you do, I'd be interested to hear back from you from the field. You know what you're seeing and what you're getting, and you know, maybe it can be incorporated into a future version of this. But my experience, unfortunately, because I don't run a WISP anymore, I don't have access to a big field test anymore, so I have to rely on all of you guys to provide feedback to help me. So I get to play in a lab environment only, which is, of course, not real world. So thank you.